you will have to enter the secret number. It'll prompt you for a number just to make sure that you're paying attention, and I can use that in order to demonstrate attendance at NTNU. So, and today we will talk about camera calibration. And if you have problems with the
NTNU Online Lecturing Support said roll call, send a direct message to NTNU Online Lecturing Support with secret number 6845. You have 5 minutes.
Okay, you can also join the Twitch stream. For Jackie Baltus. Which will also show the lecture, but it will be delayed a little. Which will also show the lecture, but it will be delayed a little. Which will also show the lecture, but and you get a nice echo effect. Which will also show the lecture, but and you get a nice echo effect. If you listen to both. So you don't want to do that. Just one of them. So today we'll be looking at camera calibration. So I started the camera calibration Jupyter notebook. We have a title, the usual prologue, and then a file with various Python routines to do 3D geometry. I just copied that in here. I'm not sure if I'm actually going to use it or not. And then we load in some standard matplotlib libraries that will come in handy later on. And the problem that we're trying to solve is an extension of what we did last class. Last class, we looked at calibration of a plane, just using the homogeneous transformations without taking perspective distortion into consideration. Today we'll be looking at the perspective distortion in the image and see what effect it has on an algorithm, the linear distance transform, which allows us to solve the camera calibration problem for three-dimensional objects and the perspective distortion. So we'll start out. We have a Rubik's Cube image that you can access. The link for the image is here. So I will download the image, or yeah, sure, I'll download it as well. And then let me think if there is if I can do that online. Okay, I just want to check if I can get the pixel coordinates here. I don't think so. options. No, there may be one, but I don't know that one. So I'll save the image. And then set up another scene. So let me just open GIMP. And add my webcam. Window. GIMP. Okay, and my webcam. So here we have that set up, and now let me just remove this one. Okay. Okay, no Discord here, never mind. So here I have the image. And now I need to get calibration points, which means I need to find mapping from image pixel coordinates to real world coordinates. Now I checked on the internet, the cube is 5.9 centimeters long and high and wide. It's a cube. So each dimension is 5.9 centimeters. So now I'll just tick off the center as good as I can for each one of the squares and then assign them the real world coordinates based on those pixel coordinates. So for example here, if I go to this square, then this should be about the center, and that would give me a coordinate of 278, 580. So I now want to generate a set of points which maps those coordinates. I want them as a NumPy array, and each point will consist of 2 entries for the image and 3 entries for the real world coordinate. Now, the distance between each point, or the distance between the cubes, is going to be 1.9 centimeters. So I'll just define that as a variable here. So if that ever changes, if I find out that the cube was set differently, different size cube, then I can easily change it here. So again, we check, and I'll make this coordinate here, the bottom coordinate with the orange and white cube. That point here should be exactly 0, 0. So let's take the first point here, 369, 585. What did I say? 366, 362. 362, 585. And the coordinate of that point would be we let x go this way, z go up, and y would be going up here then. So blue one, from white to blue is x, from orange to green is y, and from white to white is the z axis of our coordinate system. So that would mean that this point that I have here, so this should be half of 1 whole square, right? So x coordinate would be dc divided by 2. The y coordinate would be 0, and the z coordinate would also be dc divided by 2. So now we try and find the next point over, the red one. So for the red one, center I think is there, which is 450, 547. And the coordinate would be, x coordinate would be 1 dc more, right? Because we're moving one step in this direction. Z and y are not changed. Next one, over here would be 530, 505. And this would be 2 times DC. To add here, so this is the bottom row. Now let's do the coordinates in the y direction. And I will just write them all down. Here. I'll do that in one step. So first one is 278577. How about there? 206544. 544. And 140,504. So those coordinates you send a message. Okay. The first coordinate, x, would be 0, y dc over 2, and z dc over 2. Next one will be x is 0, dc over 2. I can just flip those. Because on that plane of the cube, on this plane of the cube, the x coordinate was going to be 0 for all of them. Here, y coordinate is going to be 0, and here the z coordinate is going to be 3 times dc, 5.7. Right? Because this plane here is 5.7 centimeters above the z plane. So here's the x-plane, y-plane, and z-plane. So let me get those coordinates. Switch to the GIMP. So here, let's go with this one. I already had that coordinate. That's done already. So then this one here would be about there, 364, 480. 364, 480. And the coordinates would be dc over 2 y is 0 and dc over 2 plus 1 block up. The next coordinate here 362 371 362 371 we'll have x coordinate dc over 2, y coordinate of 0, and a z coordinate of dc over 2 plus 2 times dc. And now I will add 2 points more for the z coordinate on the other part of the cube. So here I get 278 476. And the next one up would be 278 371. 371. Now the coordinates there, x would be 0, y would be dc over 2, x is 0, yes, y is dc over 2, and this would be dc over 2 plus dc. Seven, 8, 4, 7, 6. Alright, so now I have my points. I also have my graphic. So I want to plot the points first to make sure that I didn't mess up too badly with positioning them. So let's create a figure. And an axis. And then I need to get the x and y coordinates of what I want to plot. So actually, I think it was a mistake because if I want to use NumPy arrays, they need to have the same dimension in both directions. It will make things a lot easier to reason about. So I'll put them all in a single list rather than two separate lists, which means I can get rid of this one as well. Where were we? X and Y coordinates, size 30, color equals cyan, too many indices for, oh, oh, I think it would be better to plot the image first. Oof. Okay. Discord just restarted for some reason for me. Uh, can you guys hear me? Okay, then never mind. What did I plot? Ah, okay, let me do it this way. Maybe those will come in later on. Read, and URL is here. Oh, okay. So here now you can see where I assigned the points for the centers of these squares. Now the centers are not necessarily the best points. I would be able to locate them better if I would move them onto the edges of the square. Uh, these kind of points you would use if you're doing it on a calibration object. So then you would look for white and then actually calculate the white center of what your of the box that you find or the blob that you find. That will give you more pixels and a more accurate position. If you can see here, that blue dot 2 seems to be a little bit too high. So I was probably, I was in a little bit too much hurry when I did that one. So I would remeasure it. What I get here is about 534, 511. And what I set there was 530, 505. So let's change that one. 534, 511. Now what we'll actually calculate is the least squared error approximation. So as long as your error is normally distributed, it's going to work out in the end. So now I could apply the same approach that we did last time. Oh, no stream. Wait. Okay, now the stream should be up. And this is our figure. Also, you can follow the Google Collaboratory. The link is there. And also from my homepage, if you go to Teaching Computer Vision, you end up with this collaboratory here. So let's have a look and analyze what actually happens when we're dealing with perspective distortion, because if I now apply just the mapping of a plane, then clearly I'm not going to get very good results. If I think about it, the distance from here to there is larger than the distance from here to there, or here to there, or here to there, because points that are further away are going to move together. Distances that are further away from the camera back here are going to be smaller than the same distance on the front of the cube. And this is what we have to model. So that's the perspective distortion. And this applies both to humans and camera systems. Move closer together, or in other words of saying there's things that are further away from the eye camera are smaller. So let's try and analyze the effect of the perspective distortion using a simple Yeah, now the points look a little bit better, I think. So in order to understand how the perspective distortion influences the image, how the eye and the camera actually work, we will use a simple pinhole camera model. The basic idea is that we have an image plane that is mounted. So this would be your CCD or CMOS sensor, or the back of your eye. But there are some differences between the eye and the camera, just not terribly significant ones at this point. So image plane is mounted. In front of the plane, there's a lens, both for camera and the human eye. Now that lens we model as a single point. The distance that between the lens and the image plane, we'll call that distance f, and in a little bit you'll see why we call it f rather than d or something like that. And objects in front of the lens will technically speaking, light reflected from objects in front of the lens will enter the camera eye through the point lens and then strike the image sensor, the sensor. All right. So now let's draw this. Let's say that focal length f is 0.5. Then I will plot a I will plot an image plane and an object, and then we can see how the lines, how the image changes. Now the camera, I'll make it point from, oh, I'll make it point from the left edge of the screen to the right edge. And I'll have the sensor centered on the y-axis. Let's make our image plane range from let's make the image plane 2 centimeters big. So that means it will range from minus IP divided by 2 to IP divided by 2. And let's plot it in green. Color is equal to green. Right, so that's not much now. Now actually, I'll move my focal point at position 0. So that means this one will be at minus f, minus f. So now I want to plot the focal point. Which is at location 0, 0 now. Psi 30, color green. And now let's put some objects in front of the camera. Let's draw a square. Actually, yeah, a square, sure, why not? So the square, let's put it at 5, 6, 6, 5, 6, 6, or 9, 8, 5, 8, 8, 5, 5. The y coordinates, minus 2, minus 2, 2, 2, minus 2. So color is equal to red or blue. Let me see. actually I just yeah, okay. Then so move this one forward to right, then that looks a little bit better, and then I can move I think that's okay. So now we have a simplified camera model with a pinhole camera. The actual lens is here.
NTNU Online Lecturing Support said roll call, send a direct message to NTNU Online Lecturing Support with secret number 4541. You have 5 minutes.
So now I want to check what these points, I'll label these points P1, P2, P3. So this one was 5 minus 2, so 5 minus 2, call this one P1, P2, P3, P4, 5 minus 2, 8 minus 2, 8, 2, and 5, 2. So now we have P1, P2, P3, and P4. Our focal point, pinhole, that's called the focal point of the camera system. Now, if my camera looks at P1, the light reflected from P1 has to travel through exactly this point, and then the coordinate in the image plane that we're recording will be wherever that line strikes the focal point, strikes the image plane. So let's draw this one. So the line will start at point P1. Which will be 5 minus 2. Then here the distance would be minus f. And now what will be this point? That's the question. In order, right? If we can find out what that point is, then I know where the coordinate of the pixel point here. So now I can work that out. I can draw, in order to make it a little bit easier, I will plot a black sort of line that helps in the construction. Right now, that point, that line here is wrong, right? Because it doesn't go through the focal point. I just want to show how we can calculate that point, and let's do this from -f. Go to 5, yeah. That line here that goes through the center of the image plane and the focal point is called the optical axis of the camera system. And now, as you can see, I can draw a line from P1 to the focal point easily enough, because that's where it goes through. So let's plot that line there first. So now I can see that this gives me a right angled triangle. Now the ray cast from the point P1 is going to strike the image plane. So let's going to, now I have to figure out where that is here on that position. And I can do that because if I look at this triangle here and the triangle that I will generate here, then those are similar triangles. So similar triangles. Two triangles are similar if there are, if they have the same angles, if the same. Now in this figure it's easy to see why that triangle, those two triangles will be similar, because this angle and this angle here is going to be the same, right? There are two angles of a line intersection, so this angle must be the same as this angle. Oh, how come we have... here's a 90-degree angle, here's a 90-degree angle, so two of the angles are the same, which means the third angle here must also be the same. So those two angles are those two triangles are similar triangles. In our case, what is important is that the ratio of any two sides between similar triangles is going to be equal. So now let's give these some coordinates. Now when the camera is looking at a scene, then depending on your domain, the more natural way to assign the coordinate system is to have that the further away things are from the camera, that increases the z distance. So I will make this axis here my z-axis, along the optical axis. This will be my z-axis, so z increases this way. Now this point here would be the z-coordinate of the point, in our case 5. And then this is our x-coordinate. So our projection is going to be from 0, 0 to minus f. Now the ratio of 5 to minus 2, that will be flipped to be positive, so the sign changes. So if we end up with a positive coordinate over here, 5 divided by minus 2 must be the same as negative f divided by my x here. So if I flip that around, then I end up with this divided by z. So the image point u is equal to, for my point, minus 2 divided by 5 multiplied by minus f. And then that plots, can delete this one. Oh. Okay. So then this is the figure that we would get. Here you can see the line continues. The ratio minus u divided by minus f must be the same as minus 2 divided by 5, where 5 is the z coordinate and minus 2 is the x coordinate of the system. And now we can see why the same distance, if I go to 8, I'm just gonna restart Discord quickly. Let me stop streaming, disconnect. I'll be back in a minute. Robot vision, connect and stream. Let me make that one a little bit bigger, maybe 12. Here's our figure so far. You can now try and plot the line from P3 to the focal point and where it hits the image plane. So try that for yourself. Without looking at MineCode for the solution. So P3 is the point at 8.5. Oi, not 5. Right, so now we have a beam of light from P3 that goes to the focal point. That would be run to my line. Oh, and now this is projection of point P3 onto the image plane. So I can plot the coordinates. And now you can see that the distance u1 is actually much bigger than u2. So if I look at this line here, P1 to P4, it will appear much larger in my image than the line from P2 to P3. Right? So when I actually look at the new coordinate, at this u, then if I expand it, Then I have u of the point is equal to the z f. Right here, I flip the coordinate x, z, and let me try and plot an arrow there. So let's plot that at 0, 1, dx 1, dy 0. Hmm. Ooh. Let's see. Width. Right, So maybe a little bit too big. A little bit too low. So this is the Z direction, and let's move the whole thing down. Too big. 3, 4. And let's make the arrow not quite so long. So 0.5. So this is the Z direction, this is the X direction. Let me see if I can color equals blue. Oh. So here's our coordinate system, the directions, Z direction, X direction. So the image, the coordinate in the image plane divided by the Z coordinate of the point multiplied by the focal length of the point gives us our new coordinate. So then if I can use that to calculate the formulas, but before we looked at our homogeneous transformation matrices. And we talked about homogeneous coordinates. So what I want to what I would have to implement in a system in order to model the perspective distortion, that would be how can I model that? Basically, I would need to model take the x coordinate that I have, right? I can rewrite that. And just bring out the x coordinate. Sure, that's correct. Or this way. Now the second equation is going to be used in a slightly different formulation, or we can use the third one, which is the correct one. So, which is the one that's applicable to the figure that I drew here. I'll show in a second a couple of variations of how this is drawn, and then you get slightly different perspective distortion matrices. For ours, we're looking at version number 3, this one here. So the coordinates that I want, and this would be the image coordinates in the x direction, it would be the minus of xp multiplied by f multiplied by zp. So if I think about this now as homogeneous coordinates, then scaling is an affine transformation. That I can model using the following transformation matrix. right? Um, so here I scale the x and the y direction by minus f. Now if you think of this in 3 dimensions, then x is going up, z is going forward, so y will go left and right. So x and y is going to be coordinates on the image plane. Z is always going to be this distance here, which would be minus f, the way that I drew it, or 0 if I move the whole thing shifted over by f to the right. So the only coordinates that are going to be affected by the perspective distortion are the x and y coordinates, not the z coordinates. Once I project it onto an image plane, this coordinate here, the distance from the image plane to the focal point, is going to be fixed, right? That depends on the camera. So I don't get any more information from that particular point. So that means here the z coordinate is unchanged and we have 0, 0, 1. Now here I scale it by minus f, which when I look at this gives me the top part here, right? Minus f multiplied by the current x coordinate. But then I have to divide it by zp, the z coordinate of the point. So that's tricky. There's no affine transformation matrix that I can apply that will allow me to do that. However, if I use the definition of homogeneous coordinates, when we introduce the homogeneous coordinates, then I said that a point with coordinates xi, yi, and zi, and 3 coordinates, so 3-dimensional vector, we'll convert it into a 4-dimensional vector. Not I, xi. Point xi, yi is going to be remapped to a homogeneous coordinates kxi, ky, kzi, and k. And so far we've only ever done x, y, z, and 1, right? And it wasn't really clear why we would have this extension for multiple representations for a point by having an arbitrary k that we can multiply here. Now, with the... Wait, that was higher than I thought. Now, however, it comes in very handy, right? Because I now can multiply my points by minus f, and I can leave. If I now want to divide, then I can change my homogeneous transformation matrix by checking this one to 1. Because then what will happen? If I multiply the last row, I'll get 0 multiplied by x, plus 0 multiplied by y, plus 1 multiplied by z. So that gives me the z coordinate. When I multiply this here at the beginning, I get minus f times x. So this is exactly the transformation that I need here. Minus f multiplied by x divided by zp when I convert it back into homogeneous coordinates, into 3D coordinates. When I convert it out of 3D coordinates. So the perspective distortion matrix and I'll just set the points there. xi, yi, zi1.
NTNU Online Lecturing Support said roll call, send a direct message to NTNU Online Lecturing Support with secret number 4226. You have 5 minutes.
There you go. See who's still awake. How come? Left, right. Okay. Ah. So if I multiply this out, I get minus f times xi, right? For k multiply, and here the denominator is going to be 0 times x, 0 times y, 1 times z, plus 1 times 1, and that's my denominator here. Then I can divide through and I will end up with the k, the original k that I have, multiplied by this part here. Z. I have to change that to 0 here. That looks. Now this is not the only way that you see that perspective distortion matrix. Sometimes it looks a little bit different. For one thing, the negative signs are not very nice, so I can change the negative signs by a simple trick. If I look at the figure, so now my original image plane was from located at minus f, right? And it was from IP2 to minus 1. Now matplotlib line style. dotted. Okay, thought there's one solid dash dash dot offset dash 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 dot. Dot is a colon. Okay. So here, instead of having the image plane at minus f, I can move it to plus f. Right? So this would be up here. The focal point now is behind the image plane, and the coordinates actually u2 will be exactly the same, right? It's just that the sign doesn't change. Now, this version is physically not realistic. In the actual camera, in your eyes, the image flips. However, when we do the calibration, it doesn't really matter if I consider this to be plus this way or plus going the other way. So I can flip the sign easily enough. And one neat way of doing that is to move the image plane to the front. The other version of the coordinate system that you get, the other change that you get, other version of the perspective transformation matrix, you get if your focal point is not at 0, 0, but if the image plane is at 0. Because then you get z minus f basically in the equation, and you get a slightly different transformation matrix. So sometimes when you see the matrix, the perspective transformation matrix, you also get an alternative representation. This one will end up in the same result. In this case, you're just dividing by negative 1 over f for the z coordinate. So now, how does that help us with our points? I can model the camera as a compound transformation that consists of moving the camera, actually this should probably be the other way around, T and R here. Rotating the camera, then moving it to the target location, and then doing the perspective distortion. So there's a perspective distortion component or perspective projection component. There's a translation and a rotation. But at the end, I end up with 16 unknowns. Then if I have enough points, then I can find out these 16 unknowns that are part of my camera calibration matrix, given the points that I have. And that's for 3D camera calibration, what we actually need to do. Now we're using a similar approach to last class, where we did this for two-dimensional, for a single plane, without the perspective distortion. Now we need to add the perspective distortion or the perspective projection component to it. So I have to take a little break here because I need to go to the washroom quickly. So I'll be back in 2 minutes. And okay, so I'm back. Actually, I made a mistake here with my transformation matrix. I just realized, because I have to, this in itself may be a homogeneous coordinate of the form kx, kz, ky, and kx, so I need to divide by that as well. So this needs to be added to the current division that I'm doing. So this must be a 1 here, not a 0. And this is a perspective distortion matrix then. Now let's take the information that we have and try and calibrate the image of the Rubik's Cube. So now I have a set of points that are of the form ui, vi, which are the x and the y coordinates in the image plane. Z coordinate here cannot help, right? Because zp, the z coordinate on the image plane, is always 0. Then we have xi, yi, and zi. Those are the information that I get for every point. So if you checked before, where we defined the points, this would be it, right? This would be ui, vi, xi, yi, zi. So for each point now I get two equations. So the first one, and what I'm trying to find is the values of my matrix, the transformation, the compound transformation matrix. Which is a 4x4 matrix. A11, A12, A13, A14, two one, 2 2, 2 3, 2 4, 3 4, 3 3, 3 2, 3 1, 4 1, 4 2, 4 3, and 4 4. And then the equations that I get for each point and this is going to be a little bit of a monster equation now, but what the equation that I get is that ui is equal to and UI is A11 times xi plus A12 multiplied by yi plus A13 multiplied by zi plus A14. That would be x dash. Now I need to divide it by A41 for 1 by xi plus A for 2 multiplied by yi plus A for 3 multiplied by zi plus A for 4 A for 3 zi A for 4 times 1, yeah. That's UI, and then VI is A 21 22 23 24 A for 1 xy right? So these are the two equations that hold true for each point, but the problem is that ui, xi, yi, zi, and vi are all knowns. The unknowns are a11, a12, a13, a14. Those are the ones that I'm looking for, right? So I will have to rearrange these equations to convert them into a system of linear equations so that I have a11 and a12 as unknowns. So that I need to divide. Instead of dividing, I need to multiply this times VI, right? VI multiplied by this equal to that. I didn't even know you can cut cells like that. And I almost lost it. So now we get this set of equations. Now I can multiply in ui because it's known, right? And then rearrange the equation. So then it would be A11 multiplied by xi plus A12 multiplied by yi actually I don't need to multiply here, make it a bit smaller. Hey. So I'll just rearrange the A11, A12, so on and so forth. So for the first equation, I get this line, A11xi, A12yi, A13 zi plus A14. Now I need to bring over the other coordinates. Now the second row doesn't matter, right? So I get 0 multiply or A21 multiplied by 0, or no, I just convert it like that. So that'll give me minus A41, and now that should be xi ui, because ui multiplied by xi here multiplied by A41 will be negative on the other side. So negative A42 yi ui negative A for 3 zi ui negative A44 ui is equal to 0, because I brought them all over onto the other side. And then here I get 2, 1, 2, 2, 2, 3, 2, 4, and this one is unchanged, except this will be the VI's now. Now here we have all the A's separated out. I can then convert it into a calibration matrix. Or into a system of linear equations. So that would be exactly like this, except cut those out, so I end up with So this would be A11, A12, A13, A14. Now A21, 22, 23, 24 doesn't exist, doesn't occur in that equation. And then x negative xi ui negative y I ui negative z I ui and negative ui. And the next one, the next line is x, no, 0, because in the second row, second equation, A1, so on to A4 doesn't occur. So we end up with xi yi zi 1 and then we have negative x I vi negative y I vi negative z I vi negative vi. Make it a bit smaller. This is what it looks like. So then we can convert that from this matrix. If I construct, so there's more here. Right? 2 rows for every point. And the system of linear equations would be that this one multiplied by A11, A12 up to A14, A44 is equal to 0. So then this will be exactly the set of equations that we had. Now I need to find these unknowns. So we did the same thing last class for using the Boyer-Moore pseudo-inverse method to solve that system of linear equations. But it's a little bit more complicated now, because now we have a homogeneous system of linear equations. What that means is that the right side of the equation is 0. So the problem is that we now have a simple solution for this system. I can just say A11 is 0, A12 is 0, up to A44 is 0. In which case I can get a solution, right? Because then it doesn't matter what x, y, z, u, and v are. The A1s, A11, A12, if they're all 0, then I definitely end up with a solution to that equation, because everything will be 0. But we're not interested in that simple solution. What we actually need to do is, technically speaking, it's called finding the null space, finding the non-zero solutions to that system of linear equations, to that matrix. Now, since it is a homogeneous system of linear equations, and we therefore are looking for the null space, that means that there's no unique solution. Clearly, if I have a solution, A11, A12, let's say 2, 7, so on and so forth, some numbers, then any multiple of that must also be a solution, because if A11 up to A44, some numbers adds up, multiplying it through that matrix adds up being 0, then 2 times that number must also add up to 0, right? So the solution is not unique anymore. So often we select the solution where the norm is equal to 1. And that's out of habit or convenience, basically. Now the other problem that we have is that the null space may not exist if because of noise. So I end up with an over-constrained system depending on the number of points that I have. If I have an over-constrained system, then we will do the same thing we did for the previous camera calibration, the plane calibration, where we calculated the least squared error approximation. So that's done using the Penrose-Moore pseudo-inverse method. Which is actually a pretty neat trick. It's worthwhile to remember that. If you have some matrix for a system of linear equations, then pre-multiplying it by A transpose will give you the least squares squared error approximation. Okay. Now, how we find the null space is done using an algorithm called the singular value decomposition, because what we actually need is we need to find the eigenvalues. Now, depending on how many points I use, the singular value decomposition, SVD, is one of the fastest ways of calculating the null space of a matrix. Now if we go back here to the system of linear equations that we have, then we have 16 unknowns. Each point gives us 2 equations, but 2 of the points, strictly speaking, I actually know what they should be, right? A41 and A42. Those 2 elements here should be 0, 0. So I could slightly simplify this by forcing these 2 elements to 0. Usually in practice it doesn't really make much difference, so people don't bother, they just solve the system as it is, rather than otherwise you have to deal with those 2 unknowns here separately, and the equations, the implementation becomes more complicated. But we would have 14 unknowns then, right? 16 minus 2, 14. So that every point gives us 2 equations. So if you have a minimum of 7 points, then, or 8 points if you are dealing with the full 4x4 matrix, then you have enough equations to solve that system. So the minimum number of points that is required to do the calibration would be 7 or 8 if you have 0, 0 here, or 8 if you use the full 4x4 matrix. But of course, the calibration that you get will be very noisy. For practical purposes,
NTNU Online Lecturing Support said roll call. Send a direct message to NTNU Online Lecturing Support with secret number 3640. You have 5 minutes.
For practical purposes, you need to have at least 15 points to get a reasonably good calibration of your camera. And the points have to be not collinear, so they cannot all lie in a straight line. And the more they cover the space, the better it is. Starting the output field, okay. So Singular value decomposition is a very popular, very clever method for decomposing a matrix. It has actually, what it does is matrix M is decomposed into the product of three matrices M is U sigma VT. U is a unitary matrix which means it has the norm 1 and its transpose is also its inverse of eigenvectors of M transpose sigma is a diagonal matrix of the square root of the eigenvectors, eigenvalues of MTM and MMT. These they are usually ordered by magnitude. So the largest one is at row 0, column 0. The smaller ones are at row n, column n. V is a unitary matrix of eigenvectors of M T M. Now, for our calibration purposes, we're interested in the solution with the smallest eigenvalues for MTM, because that's the least squared approximation, right? AT multiplied by A. So that's what we want to find the null space for. That's a matrix that we need to find the null space for. So that corresponds to the last column of the matrix VT. Or the last row of matrix V. Right? Because the transpose, the column, will become the last row. Okay, so now let's have a look and see how that works on our points. Here, when I looked at the points for the cube, I now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need a minimum of 8. Of course, if I calibrate for the other, if I add the other points in here too, then I will get a much better calibration. I just let you do that as a homework. Then you can see whether you can improve the calibration system or not. So first what I have to do is I have to generate the my calibration matrix. Then I extract the points U, V, X, Y, Z. X, Y, Z is equal to P. Let me just double check to make sure I added those correctly. Where are my points? Here, U, V, X, Y, Z. Yeah. P. So then for every point I add 2 rows to my matrix. The first row is equal to a list. And the list will be X, Y, and Z 1, then 0, 0, 0. X, Y, Z 1, 0, 0, 0, 0. 2, 3, 4 zeros. And then negative X, U, negative Y, U, negative Z, U, and negative U. Times U, negative Y times U, negative Z times U, and negative U. So that's what I want to, that's the first one that I add to my transformation matrix. And then the next row just in case we need to print them out later on. Next one will be 0, 0, 0, 0, 4 zeros, and then X, Y, Z 1, negative X, V, 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 V. To match the second equation that we have here. right? 0, 0, 0, 0, x, y, z, 1, negative x, v, negative y, v, negative z, v, negative v. Then I'll take that and convert that list into a NumPy array. So then we just print a here. So that works. 1, 2, 3, 4, 5, 10, 11, 12. Okay, come on into 1, 2. Come I ended up with 12 unknowns now here all of a sudden. Ah, yes. There's only 12 unknowns, and yes, I made a mistake. There's only 12 unknowns in the system because in our transformation matrix, the third row here, this row doesn't really matter, right? Because that will collapse to 0. So A3, 1, 3, 2, 3, 3, and 3, 4 are not important. So we can leave them out of the system of linear equations. So we only have 12 unknowns. Each equation gives us, each point gives us 2 equations, so I need 6 points in order to be able to calibrate that. Minimum of 6 points, but in practice you need to have at least, or in practice you need to have at least 15 points to get a good calibration. So now we don't have to implement the singular value decomposition, luckily. That one is actually done by, that one is implemented in NumPy linalg package. So we can check what the parameters are. That gives us, I have to pass in a matrix A. And it provides us with the U array first, then the scaling factor, and then VH. The transpose of the V matrix. I guess I can call that VT. U S and VT. So here's our matrix U, the set of eigenvectors for, which one is it, MT, set of eigenvectors for MMT. So that'd be a 12 by 12 matrix. Then we have S, which is a diagonal matrix of eigenvalues sorted by size. So the first one is 5,200, 3,600, 2,700, 604, 9.2, 5.81, 4.89, 1.1, 0.69, 0.43, 0.31, and a 0.88, 0.0082. And here's our matrix VT. Now what we're interested in is the last column, which would be this one, the last entry that we have for each one of those. That will be a solution for our camera calibration problem. Okay, let me just check what it returns. So I guess would be VT this would be the solution then, the last element of the second row. I just print out VT0, VT1. So now let's see what we get. A for so I need 3 rows with 4 columns. No, should be 12. Missed one, 20, 12. Okay, 20, 12. So I have 10 points. I get 20 rows, 12 unknowns. And then I reshape that into a 3 by 4 solution matrix. Then if I want to find that, that gives me so I can take my first point and the coordinates that I used were DC2 I have to convert it into homogeneous coordinates, so I need to add a 1 to it. And then let's calculate the P dash, which will be solution dot solution dot point point dash so 0.95 centimeters 0 and 0.95 1 gives us 1.14 negative 266 7.60 so then PTD U would be PTD 0 divided by PTD 2 no 0 1 2 yeah V would be PTD 0 divide 0 1 divided by PTD 2 because now I have to convert them from homogeneous coordinates to image coordinates. Negative 0.35. So that means that the calibration is not very good. It also means that I must have missed one of the points. So I'll have to double check the points that I ordered, that I added here to make sure that I read off the coordinates correctly. You should try that on your own with the you should try that on your own with the Rubik's Cube. Also make sure that the dimensions are correct when so you should measure the size of the cube. Based on that, then you can calculate the displacement, the relative pose of the cube to your camera, as well as the focal length of your camera. I know what the problem is. Right, the points are the UV coordinates that I passed in are actually incorrect. I will have to fix that next class. I took the actual image coordinates. What you really have to take is the distance from the optical center of the image sensor. So this should be 0 0 here. I have 0 0 up here somewhere, and that translation then, I think that makes the computation, even though in theory it should work, it makes it very unstable. You get better results if you actually reformat the points, remap them to a point cloud that is centered at the mean and has sort of an average distance. And right now the centimeters are too small compared to the coordinates, and I think that's why it's unstable. So when we actually do the points, The image coordinates that I printed out was where are the image size points? (800 by 647). So 800 rows, 647 pixels across. Where are my points? So now here UC/VC is this, then UC is equal to, and I'm not sure how this should be I height, I width. So U is UC is UC minus I height over 2. And V is I width minus 2. So now if it's exactly the center, okay. Now we get a solution. Not much better. Plus So usually we do this to the image. Does that actually solve it? But I think this here is wrong. Okay, good. So that's not. Okay, so it actually prints out exact V, not V transpose. So we need to take the last row, not the last column, and then here are the coordinates that we get using our calibration. So as homework, you should try and plot in, as a little exercise, you can draw in the lines for the Rubik's Cube, and then you can see how good our calibration is. And then you can see it's always very fragile if you only have a number of points. If you add in the other points for the cube, then you can improve the calibration a lot for your cube. But this is how you can calculate the pixel coordinates that you get for the points. And I just want to make sure U is height. Yeah. Okay. So I need to add this to it. Yeah. Okay, good. That's it for today. So next week we will finish off camera calibration. We'll actually draw the lines for the cube, or you will draw the lines until next week. And then we'll look at edge detection very briefly, because I think most of you have already some experience with edge detection. And we'll look at the mixture of Gaussian background removal algorithm, because the given circumstances mean that algorithm actually will allow me to do something pretty neat that I will try and show to you next class. So that's it for today. Thank you for listening, and now hopefully you can use the camera from your robot in a more accurate way. You'll be able to find the distance of obstacles to your robot very much easier or more accurately than other models. I've seen some students that just applied a neural network to the problem of camera calibration, but since this is a straight geometrical problem, neural networks are actually not a good tool, because unless you can get pixels over the entire viewing field of your camera and they're all calibrated, the neural network will do a poorer job generalizing to the general theme than your camera calibration algorithm would do. Plus you would have to collect a lot more points to be able to train the network at all. So that's it for today, and I'll see you all next Monday then. So bye bye. Also, the midterm will be in 2 weeks. Oh.